In this video, we learn how to solve Byzantine agreement in an asynchronous network, where messages arrive after arbitrary delays. We assume you are familiar with Byzantine agreement, where n nodes with inputs must reach agreement despite the presence of Byzantine nodes which can act maliciously, for example by sending incorrect messages. Nevertheless, let's recap the three properties a Byzantine agreement algorithm must satisfy. The first property, agreement, says that all correct nodes, that is, all nodes that are not Byzantine, must decide on the same value. Then, the second property, validity, connects the inputs and the outputs. It says that if the correct nodes begin with a common input, then they must decide on this input. Finally, the third property, termination, says that all correct nodes must eventually decide on a value. Our goal in this video is to solve Byzantine agreement in an asynchronous network. In an asynchronous network, once a node sends a message, there is no bound on how long it takes for the message to arrive at its destination. The only guarantee is that the message eventually arrives. The weakness of this guarantee results in additional challenges. We demonstrate the most major one with the example here, where node B is waiting for node A's slow message. This seems fine, after all, the message will eventually arrive. And yet, an asynchronous Byzantine agreement algorithm cannot allow the nodes to wait forever for each other's messages. Can you see why? Please pause the video for a moment to think about this. The issue is that node A could actually be a Byzantine node who has not sent any message. In this case, B would wait forever to hear from A, and fail to terminate. What B can do in an asynchronous network is wait for sufficiently many messages. For example, if there exist three nodes which should send B messages, and at most one of these three nodes is Byzantine, then B will receive at least two messages for sure, and so it can wait for two messages. Our Byzantine agreement algorithm will involve waiting instructions like this. Without further ado, let's learn the Ben-Or algorithm, which in an asynchronous network, solves Byzantine agreement on binary inputs when the maximum number f of Byzantine nodes is less than n over 10. Note that there do exist asynchronous Byzantine agreement algorithms which optimally only require f to be less than n over 3. However, these algorithms typically involve more steps than fit in a video. The Ben-Or algorithm consists of rounds. These rounds do not correspond to time intervals as they would in a synchronous algorithm. Instead, they correspond to iteration counts that each node individually keeps track of. Let's pick some arbitrary round R and study how it works. This is enough to learn how the algorithm works, because the rounds of the Ben-Or algorithm are all identical. To understand the algorithm, let's pick an arbitrary node and see how it behaves in round R. The node has a preferred output x, which it proposes by broadcasting propose xr. Note that the proposal is tagged with the round R so that everyone can tell in which round the node has proposed x, no matter when they receive the proposal. After proposing its bit, the node waits until it receives n-f round R proposals. It is safe for the node to do this, because even if the Byzantine nodes never propose anything, the node is guaranteed to receive n-f proposals after n-f correct nodes propose their bits. Upon receiving n-f proposals, the node lets y be the bit it has seen proposed most often, breaking any tie between 0 and 1 arbitrarily. Then, the node decides on how to proceed depending on whether it has received proposals on y from more than n over 2 plus 3f nodes, more than n over 2 plus f nodes, or at most n over 2 plus f nodes. If the node has received more than n over 2 plus 3f proposals on y, then it has observed an overwhelming majority preference for the output y. Hence, the node outputs y, proposes y in round R plus 1, and terminates. The proposal here ensures that every correct node proposes in round R plus 1, so that no nodes get stuck waiting for n-f proposals in round R plus 1. The rounds R plus 2 and onwards are of no concern, because we will show that if some correct node terminates in any round, then every correct node terminates at the latest in the next round. If the node has received more than n over 2 plus f, but not more than n over 2 plus 3f proposals on y, then it has observed a weaker, but still significant majority preference for the output y. Hence, the node conforms to the majority and updates its bit to y before advancing to round R plus 1. Finally, if the node has received at most n over 2 plus f proposals on y, then it has not observed a clear majority preference for any output. In this final scenario, the node flips a coin and chooses its round r+1 bit uniformly at random. The randomness here is crucial, as it is how the Byzantine algorithm circumvents the FLP impossibility result, which states that a deterministic asynchronous Byzantine agreement algorithm cannot tolerate even a single node crashing, and thus requires asynchronous Byzantine agreement algorithms to be randomized. With that, the algorithm is complete. Each correct node begins round 1, preferring its input, and then repeatedly proposes bits every round until it terminates in some round upon receiving n over 2 plus 3f proposals on some bit. What remains to show now is that the algorithm is correct. Let's begin with validity. It follows from the stronger guarantee that if in any round more than n over 2 plus 4f correct nodes propose some common bit x, then at the end of the round, every correct node outputs x. This is because by waiting for n-f proposals during the round, the correct nodes receive all but at most f of the correct proposals on x and thus receive more than n over 2 plus 3f proposals on x, which is enough for them to output x. The guarantee implies validity because f being less than n over 10 implies that n-f is greater than n over 2 plus 4f, which means that there exist more than n over 2 plus 4f correct nodes. Hence, if the correct nodes have some common input x, then in the very first round they all propose x, output x and terminate. As for agreement, suppose there exists some first round R where some correct node A outputs. In round R, A receives n over 2 plus 3f proposals on some bit y, proposes y with the round tag r+1, outputs y, and terminates. Consider now the perspective of any other correct node B in round R. How many proposals on y is B guaranteed to receive? Please pause the video and see if you can figure out the answer yourself. Well, since A received more than n over 2 plus 3f proposals on y, we know that A received proposals on y from more than n over 2 plus 2f correct nodes. By waiting for n-f proposals, B receives proposals from all but f of these more than n over 2 plus 2f correct nodes who proposed y. Hence, B receives more than n over 2 plus f proposals on y. That is great news, because we can now constrain what B does at the end of the round. The first possibility is that B receives more than n over 2 plus 3f proposals on y, like A did. Then, B also proposes y with the round tag r+1, outputs y and terminates. Alternatively, B might receive more than n over 2 plus f, but not more than n over 2 plus 3f proposals on y. Then, B updates its bit to y, and proposes y in round r+1. In either case, B proposes y in round r+1. Since B was an arbitrary correct node, we conclude that every correct node outputs y and terminates, either in round R by receiving more than n over 2 plus 3f proposals on y, or in round r+1 because every correct node proposes y in round r+1. We are not done yet, because we need to show that in some round, some correct node will receive more than n over 2 plus 3f proposals on some bit. We argue that this is because the correct nodes update their bits randomly when they are indecisive. Suppose for any round R which every correct node runs that there exists a bit x such that the nodes can receive more than n over 2 plus f round R proposals only on x. Then, in round R, each correct node updates its bit to x with probability either 1 or 1 over 2. With some luck, this should result in more than n over 2 plus 4f correct nodes updating their bits to x and proposing it, and thus result in agreement on x. So, we only need to show that for every round there indeed exists such a bit. But before we do so, please pause the video and see if you can figure out why this is the case yourself. Well, suppose for the sake of contradiction that there exists no such bit. Then, while some nodes receive more than n over 2 plus f proposals on some bit x, some other nodes receive more than n over 2 plus f proposals on the other bit y. Hence, there exist more than n over 2 correct nodes who have proposed x, and more than n over 2 correct nodes who have proposed y. However, because a correct node cannot propose both x and y, we conclude that there exist more than n correct nodes, a contradiction. Alright, we have established that in each round there is a chance that the nodes will get lucky and reach agreement. However, what are the odds? If we assume that f is roughly n over 10, then the probability that the node's random bits are skewed enough in any direction to guarantee agreement decreases exponentially with n. Hence, the algorithm takes exponentially many rounds in expectation. Terrible. However, if f is actually proportional to the square root of n, then we do not need such a massive skew. In this case, the probability is lower bounded by a constant, and thus, agreement takes a constant number of rounds in expectation. Note that the trade-off here is just a shortcoming of the Ben-Or algorithm. There do exist more advanced algorithms which simultaneously tolerate many Byzantine nodes and terminate quickly. Let's summarize what we've learnt. We considered the Byzantine agreement problem, where the correct nodes must reach agreement in the presence of Byzantine nodes that behave as they wish. Then, we discussed asynchronous networks, where messages arrive after arbitrary delays, and discussed why an asynchronous Byzantine agreement algorithm cannot involve indefinite waits for all messages. Finally, we saw that asynchronous Byzantine agreement is possible by learning the Ben-Or algorithm, which solves Byzantine agreement in an asynchronous network of n nodes where up to f nodes are Byzantine as long as f is less than n over 10, albeit in exponentially many rounds unless f is minuscule compared to n. Thanks for watching this video.